Hi, good morning. This is a video explaining your performance tasks. So, first of all, take note that we have two devices. You can have curved mirrors and lenses. And notice that um, curved mirrors can be two types. You can have a concave mirror and you can have a convex mirror. And then lenses also are two types. You can have a concave lens and obviously a convex lens. Okay. And in each case, you can have five cases. I mean, in each type of device, like a concave mirror, you can have five cases, which is if the object is placed beyond C, if the object is placed at C, if the object is placed between F and C, if the object is placed at F, or if the object is placed between F and V, right? Now, for lenses, it's the same. Only one terminology differs, which is instead of C, we call it beyond 2F. If the object is at 2F, if the object is between F and 2F, and if the object is at F, and if the object is between F and V. Okay? So all in all, class, if this was a real, face-to-face class, I would have wanted you to do all of this. So five cases for convex mirror, five cases for concave mirror, five cases for concave lens, and five cases for convex lens. So that would make it a total of 20 diagrams, right? And then each of those diagrams, you have to calculate also using the mathematical method and prove to me that the diagram and the mathematical method do indeed agree on the results. Okay. However, given the face to face situation that we have, I deem it too numerous if I assign you 20 diagrams. So, what I'll do is you will just be assigned to one type of device. Either you're assigned to a concave mirror, convex lens, concave lens, or convex mirror. So that means you will only draw five diagrams. So and that's a fourth, one fourth of the task, right? Instead of 20, one fourth, lima na lang. But you will still do the mathematical solution and the ray diagramming. Okay. Now, what will be your assignment? That would be discussed. Uh, that will be told to you during the synchronous class so that you will know which is your assignment. So it could be that you are assigned for a concave lens and you do five cases and that's it. Or it could be that you're assigned for a convex mirror and that would be your assignment. Okay? Now, for mirrors, let me remind you, I have discussed this a lot of times, but let me remind you for a mirror, you have to base your curve on a real circle. So you have to use something like a drawing compass for this. Choose a center of curvature somewhere here, and then choose how far that center of curvature is from the vertex. So let's say you decide it would be 5 inches or so. So get a ruler, measure 5 inches. Make sure the pen is on 0 and the anchor of the compass is on 5 inches, something like that. And then now you can start making your curve. This step is important, class, because if you don't get the curve right, your diagram might be erroneous. And again, even this is already tricky because, again, as I told you, the perfect mirror would have been a parabolic surface, but we are just approximating it using a surface of a circle or the curve of a circle. So even a perfect circle is already inherent for it's already having errors because of it not being parabolic. So somewhat na if you just make your curve and not a perfect one, right? You just make your curve and not a curve of a circle. Now again from here, notice that you have the center of curvature here. So your focus here should be halfway between. So if you set it to be 5 inches, this must be 2 inches away. So let me get this straight. You decide how far it is. You could use 10 centimeters for all like for your case. Um, you could use 4 centimeters, 3 centimeters. It's up to you. I am giving you free will because I want you to realize that this thing really works for all situations, not just for situations for examples that I give you. Okay, so that's the essence why you have to make them, and it makes it a little bit more challenging than just me giving you a diagram that you draw on, right? So it's a little bit more challenging. So you do that, and then you put your object, and again you have 5 cases: beyond C, which is beyond C, at C itself, between F and C, at F itself, and between F and V for a convex for a concave um, for a concave case. Now for a convex case, because you are going to put the object somewhere here, right? Because you're using the convex side. It's still the same beyond C, but it's not really the object is at a location that is beyond C. You can say it is in front of the mirror at a distance equivalent to beyond C. So you take this, you take the distance, you place it here. So for example, that is 5 centimeters, 5 inches, man. So you could decide that you place the object at 7 inches away. And again, unsa mo jay gamiton ng distance, sir? You decide. That's why I'm giving you the power. As long as it falls under the category beyond C. Okay, so for example, 7 centimeters, 7 centimeters, that's beyond C. But if you're using a convex mirror, you place it here. But if you're using a concave mirror, you're using this side, you place it here. But if you're using a convex mirror, that's not a convex mirror, man. So you place it the same distance, but move it here. So that's why technically we call it a distance that is in front of the mirror equivalent to beyond C. Equivalent to meaning it's not really beyond C because beyond C is inside, but it's equivalent, a distance that is equivalent, right? But still the same, beyond C, at C, between F and C, at F, between F and V, because obviously this is your vertex here. Okay? Now, how about the height, sir? Again, you decide. I'm giving you power so that you can really say that because it's more on you convincing yourself that this mathematical method or ray diagramming really works. Okay, so if you decide, for example, that your image will be 2 inches high, that's no problem, 2 inches high. But again, I would recommend that your object height would be smaller compared to your radius. So to your focal length. So for example, if this is your focal length, that length, if your object is comparable to or near the focal length in terms of length, I would argue that because of the non-parabolic curve, it would affect your image. So make your the height of the object smaller compared to the curvature of the circle so that it still approximates the parabolic surface. Okay? Again, you decide the curve, you decide how far the F is and the C is using your compass. You decide the height of the object, but I only ask that you do the 5 cases, which means it should be somewhere beyond C, at C, between F and C, at F, and between F and V. Again, if it's a concave mirror, you place it here. If it's a convex mirror, then it will be a distance that is equivalent to the things I mentioned, but on this side. Okay? Mo na siya. Now, for a lens, still the same. You are going to make this line, principal axis, and then you have to make a vertical line, and that represents your lens axis. And for your lens axis, for making your lens, it's not as tedious as the mirrors, because the mirrors you have to copy the exact shape of the surface of the or the shape, the curve of the circle. In this case, you don't need to, because what you need is just the lens axis. Obviously, if you have to make it a concave lens, then do it like this. But the curve, this curve, it doesn't matter what this shape is. I mean, how curvy it is, it doesn't matter. If you are using a convex lens, then you just make a curve like that. Okay? And again, from there, you decide what should be my f. Is it like this? So my f is here, my 2f is here. Or is it this short? My f is here, my 2f is here. It depends on you. You decide. I'm giving you that control so that you realize that this applies to all situations. So in my case, I will decide that f is here, 2f is here. And again, for lenses, those f and 2f exist on both sides, because if you place the object here, you know, it still works. It still refracts the light rays. If you place the object here, it still works. So therefore, the f and the 2f's will exist on both sides. So here it changes. Instead of beyond C, because there's no center of curvature here, you have beyond 2F. At 2F, between F and 2F, at F, and between F and the vertex, of course. So this is F, this is 2F. And again, you decide the height of the object. In this case, this is not, because we are not using a curve class. The height of the object is not sensitive. You can totally make a height that is bigger or smaller. It doesn't uh, affect the image that is formed. But you get to decide what that is. I only ask that you do one example that falls under this category. So one for each case, right? And then, and then again, I feel like I have not emphasized this well enough, but if you have a lens, the lens axis is important there, because if you have an object here, and then let's say this is the F here, and then you are doing parallel focus ray, so you draw the light ray here, you do not stop at the surface of the lens. What you do is you only stop when you hit the lens axis. And then when you hit the lens axis, that's when you change the direction of the light rays downwards. And it should pass through the focus. Okay? Now, I want to be careful here. I want you to realize that when we discussed refraction, we basically discussed it and said it is the changing of the direction of light rays as it passes through two boundaries. As it passes to the boundary of two media. And because of that, notice that the light ray here is traveling in air, right? And then here, obviously, the lens is glass. And then outside the glass is obviously air. So what happens is light ray enters the boundary between air and glass. Okay? And then as it exits here, it also changes direction, because it's now the boundary between air and glass. So strictly speaking, this should be what happens in reality. Light ray hits the boundary, it changes direction, okay? And then as it exits the air, as it exits the glass to the air, that's another boundary. And because that's another boundary, there's another change in direction. So look at the difference of this one. This one is lens axis, and then you only change direction once. This one is the more realistic scenario. So what really happens is it enters the boundary between the two, changes direction, and because now it's again a boundary between glass and air, it changes direction again. But what I'm trying to say is this class is difficult to do, because you have to judge what angle it will change as it enters this boundary, and you have to judge what angle would be changed as it exits this second boundary. What we're saying is, if we just have this light ray pass through and hit the lens axis, like so, and then bend at the center, it's the same. You achieve the same result. So what we're trying to say is, yes, in reality, what really happens is it bends and then bends. There's actually two bends. But for practicality's sake, it's easier to assume that the light ray only changes direction when it reaches the lens axis. Okay? So in other words, this technique is kind of a cheat. This is kind of a shortcut that we do to make our lives easier. But it doesn't change the fact that in the real world, what really happens is the light ray changes direction as it passes through this boundary and then changes direction again as it exits this boundary. So there is two changes in direction. It just so happened that if we assume that the light rays hit the lens axis first before it changes direction, just so happens that we achieve the same result. So again, balik ko na ho, this is kind of a cheat that it's way easier to do than this. That's why we do it. Okay? So again, uh, you assume that the light rays hit the lens axis before changing direction. In this case, I'm doing an FP ray. Okay, so I hope you understand that there are nuances like that. There are shortcuts like that that we take in science because we don't want things to be more complicated. Because in higher concept, really here, you have to look at a law called the Snell's law, wherein you measure the angle, the incident angle here, and then you measure the refracted angle, and the incident angle and the refracted angle has a certain relationship, and that's called the Snell's law. And you have to do some calculations there to just to get where this light ray would bend towards, and then as it exits here, another Snell's law. So it's much tedious than if we just cheat a little bit. We cheat a little bit by just assuming that light rays only change direction when it hits the lens axis. But again, true to the concept of refraction, as it enters the boundary between the two, it bends a little. As it exits the boundary between the two, it bends a little. So there are two changes in directions here. But again, we encapsulate that. We take a shortcut of that by assuming that it behaves like this. Okay? So finally, once you have that, what I want you to do is I'm just quickly make a ray diagram here. P, F ray, V ray, F, P ray. Maybe they meet here. Create the object here. After that, I'm sorry. Wadi mo kita. So you have PF ray, V ray, FP ray, and maybe you create an image here. After that, you always determine the object location and then the image lost. Location, orientation, size, and type. That's for the diagram. At the back of the paper, you have to do the mathematical calculation, and that is you will have to write the H, what that is in your given. You have to measure. So, for example, I'm just making an example here. Here, you have to determine the P, which is always positive. Let's say it's 5 centimeters away. You have to determine the F, and again, remember you set this F. You are the one in control. So my F may be, let's say I'm using a concave lens. Concave lens has a negative F, remember? So 3 cm like that. And then from there, you can calculate for the Q first and then calculate for the H prime next. But you don't stop there. After you do that, you still give me object location. What would that be? And then you still give me the image things, which is the lost. And again, the idea here is to find out if the results that you have here are the same as the results that you have in the ray diagram. So I would say it's quite a lengthy task because you will do 5 things, 5 diagrams, and 5 calculations. But remember, this is originally 20 tasks. I am cutting out 3/4 of the work. so that you will only do one fourth of the work. So please understand. I know we have only 1 week left in the second quarter, but I believe that if you do one diagram per day, right? One calculation per day, and if you collaborate with your classmates, obviously this is an open thing to do. You can collaborate with your classmates as long as you don't copy the exact um, case of your classmates, because I would know if gikopya, because remember, you get to decide your curvature, you get to decide your focus, you get to decide your 2f, your f, your so if everything is the same, parehang 2f, parehang c, parehang height, then it would tell me that there's no originality there, right? So I hope that guides you. So again, your output will be 5 diagrams with calculations. The diagram will have image location and the image lost. The calculations would have the image location and the image lost. And more or less, the values of the two would be the same. Obviously, there will be maybe some differences a little bit. Like maybe in your ray diagram, when you measure the image, it's 3 cm, but in the calculation, it's 3.5 cm. It doesn't matter if the difference is just very minimal. Because again, in the first place, we're not using parabolic curves. So there should be some errors, but a little, as little as possible. Okay. So how would you submit this? Well, I would suggest you do it on hard paper. You draw it and then you take a clear picture and then upload it to the facility that I am posting in MrHelp.net. If you are quite techy, you can actually do the diagrams using Word. I have done it myself using the lines in Word, but it might be too much for most of you who are not into technology or PC stuff. But either way, you can do that. This is posted in MrHelp.net. Okay, so again, if you have more questions to ask me, please do not hesitate to contact me some messenger. Okay, that would be all for you. Again, your assignments, that depends on your section. So will I do a concave lens, concave mirror, and so on and so forth? That depends on what I give you during the synchronous class. So during the synchronous class, I will tell you what the assignment will be for each section. So you don't copy how I assign the devices to Copernicus will be different from how I assign it to Newton and to the other sections. So don't just copy what the scheme I'm using for the other sections. Okay? So I hope that guides you about the performance task, the one-time big time performance task for the second quarter. And that would be all. Goodbye.